Chapter 3. From Structure to Behavior. Defining Behavioral Architecture. Behavior is commonly treated as an output of personality or emotion. In architectural cognition, behavior is an expression of structure. Structure refers to the internal organization of models, predictions, and decision pathways. When structure is stable, behavior becomes consistent. When structure is fragmented, behavior appears chaotic or reactive. This distinction shifts the focus away from traits and toward computation. From the outside, behavior seems spontaneous. A human speaks, moves, or reacts without visible processing. Internally, these actions are the end of a long chain. Sensory data is encoded, evaluated against predictive models, routed through relevance filters, and transformed into motor or linguistic output. Most of this sequence never enters awareness. Consciousness witnesses the final product and assumes it was voluntary. In reality, architecture has already executed the core computation. This structural view matters because behavior does not originate at the moment of action. It originates at the moment of interpretation. When sensory input enters the system, the architecture evaluates what it is, what it means, and what should follow. Two individuals can receive identical input, but produce different behavior because their structures are different. One architecture predicts threat, another predicts opportunity, another predicts irrelevance. The output diverges not because of emotion, but because of models. Over time, behavior creates a feedback loop. Repeated output reinforces or weakens certain pathways. If an action yields a stable and positive result, the architecture flags that pathway as reliable. If an action yields instability or penalty, the pathway becomes less favored. This is not motivation. It is optimization. Behavioral patterns are the visible residue of internal architecture refining itself. The transition from structure to behavior introduces a new domain of cognition, action selection. Action selection is the mechanism by which the system chooses one behavioral trajectory over another. This is not free choice in the philosophical sense. It is computation over constraints. The architecture evaluates predicted outcomes, cost, risk, timing, and relevance. The winning pathway becomes behavior. Understanding behavior at this level makes it predictable without reducing it to stereotypes. It becomes predictable because architecture is consistent. When structure changes, behavior changes. When behavior changes without structural change, the change is temporary. When structural change precedes behavioral change, the change is stable. In this chapter, we examine how architecture scales into visible action without invoking identity or emotion. Behavior is not the surface layer of personality. It is the externalization of internal computation, interpreting input and selecting action. Before behavior becomes visible, the system must interpret incoming information and decide how to respond. Interpretation is the internal process that determines what the input represents. It is not simple recognition. It is classification. A sound, a phrase, a gesture, or an event enters the system, and the architecture evaluates what category it belongs to, what relevance it has, and what constraints it imposes. This evaluation happens before any action is produced. Internally, interpretation begins with sensory encoding. The raw data is converted into neural patterns. These patterns are then compared against predictive models. A model attempts to forecast what will happen next and what the input means for the current state. If the input matches a known pattern, the model stabilizes. If it does not, the model may generate uncertainty signals. These signals are not emotional. They are informational. They indicate that the input requires additional computation. After interpretation, the system must perform action selection. Action selection is the mechanism through which the architecture determines what should follow the interpretation. It is not spontaneous. It is competitive. Multiple possible actions exist simultaneously. Each action carries different predicted outcomes, different costs, and different time horizons. The architecture evaluates these possibilities and selects the one that aligns with the internal constraints. Externally, this process is invisible. A person may speak, remain silent, move, refuse to move, comply, or resist. These behaviors appear to be driven by impulse or personality. Internally, they are the result of a constraint satisfaction process. Constraints include predicted consequences, social context, physical capability, available time, and internal models. When a selected action appears irrational, it often means that the observer does not have access to the constraints the system was using during evaluation. Interpretation and action selection are tightly coupled. A system that interprets input incorrectly will select actions that appear inappropriate or misaligned. A system that interprets input accurately but selects actions poorly will appear inconsistent or unstable. A system that performs both consistently will produce behavior that seems efficient and coherent. This architectural framing moves behavior out of the realm of spontaneity. It does not deny agency. It clarifies that agency operates through computation rather than impulse. The visible action is only the final stage. The critical transformation occurs earlier, when input is interpreted and selection pathways are evaluated. Constraint architecture and behavioral output. Once interpretation and action selection are understood as computational processes, a final foundation layer must be defined before behavior can be examined at scale. This layer is constraint architecture. Constraints are not limitations in the emotional sense. They are boundary conditions that influence which actions remain viable after interpretation. Every system operates under constraints. They determine which trajectories are computationally possible and which are not. Internally, constraints include predictive confidence, available knowledge, motor capability, temporal horizons, and environmental relevance. These are not subjective. They are structural factors that narrow the set of possible actions. If an action carries insufficient predictive confidence, the system may discard it. If an action exceeds the current knowledge structure, the system may suspend it. If an action is not viable under time constraints, the system may favor a faster alternative. Constraint architecture determines how many options survive this filtration. Externally, constraint architecture explains why behavior often appears limited or predictable, even in complex organisms. Observers may interpret this predictability as habit or personality. In computational terms, predictability emerges because constraints produce stable filtering rules. A system that repeatedly evaluates similar contexts under similar constraints will repeatedly produce similar behavior. No emotional continuity is required. The architecture alone is sufficient to generate consistency. Constraint architecture also explains why behavior changes slowly. When a system acquires new knowledge, improves predictive models, or shifts temporal horizons, the constraints change. Behavioral options that were previously filtered out become viable. This produces behavioral expansion. Conversely, when constraints tighten, behavioral options collapse. This produces behavioral reduction. In both cases, the architecture determines the range of visible behavior long before any external action occurs. Internally, constraint architecture interacts with interpretation and action selection as a sequence. Interpretation defines input. Action selection proposes possible outputs. Constraints filter proposals. The surviving trajectory becomes behavior. This sequence occurs continuously, without conscious participation. Conscious awareness observes the result and constructs a narrative after the computation has already completed. This narrative can be useful socially, but it does not describe the mechanism. By defining constraint architecture, the foundation layer of behavioral cognition becomes complete. Interpretation explains how input is structured. Action selection explains how possible outputs are generated. Constraints explain why only certain outputs become real. With these components established, behavior can now be examined as a scaled expression of architecture, rather than as a surface phenomenon. Emergence of automatic patterns. Patterns do not begin as patterns. They begin as individual selections that share similar conditions. When the architecture encounters comparable inputs, and when constraints favor similar outputs, convergence occurs. This convergence is not directed by intention. It is driven by computation. The system seeks stability because stability minimizes cost. Cost is reduced when the architecture does not need to calculate from zero every time. As selections repeat, the system stores the intermediate components of those calculations. Over time, the selection process becomes shorter. Eventually, it becomes automatic. Automaticity is not a psychological construct. It is a structural property. It means less computation is required to produce the same output under similar conditions. The architecture optimizes for efficiency because efficiency conserves resources. This optimization produces the appearance of preference or habit. Externally, it looks like behavior. Internally, it is the conservation of processing. Constraint architecture plays a central role in this transition. When constraints remain stable, the range of viable selections narrows. A narrow range produces repetition. Repetition generates predictability. Predictability reduces uncertainty. When uncertainty drops, the architecture invests less processing into evaluation. It begins to anticipate rather than compute. Anticipation accelerates selection. This acceleration is perceived from outside as automatic behavior, but internally, it is a reduction in processing complexity. As the architecture reduces computation, it also reduces variability. Variability is expensive. Stability is cheap. When variability decreases, behavior becomes consistent. Consistency is a surface-level phenomenon. Underneath that surface, countless evaluations have already taken place, but most of them have been eliminated before reaching awareness. Only the final output is visible. The internal computation that produced it is silent. Over time, this silence becomes the dominant mode. Another property emerges during this transition. As patterns stabilize, they begin to operate across longer time spans. This is not because the system plans ahead, but because stability allows the system to project forward with fewer unknowns. The architecture builds internal predictions, not in language, but in computed expectations. These expectations influence selection before selection occurs. This mechanism produces what appears to be preparation. From the outside, it looks like foresight. Internally, it is simply low-cost prediction. Automatic patterns do not require conscious participation. The architecture will form them even without awareness. It will refine them without awareness. It will deploy them without awareness. This lack of awareness does not indicate complexity or intelligence. It indicates efficiency. When efficiency reaches a threshold, involvement becomes unnecessary. The system has already calculated the most probable outputs and cached the pathways required to reach them. These patterns are visible in any sustained environment. In controlled environments, they are easier to detect because noise is reduced. In noisy environments, they take longer to stabilize because competing constraints interfere with selection. However, given enough repetition and enough constraint stability, they will emerge. The architecture cannot avoid optimization because optimization is a function of survival in computational systems. Eventually, these automatic patterns reach a point where they interact with one another. They begin to influence selection at higher levels. This interaction layer is where external observers begin to interpret personality, preference, discipline, or habit. None of these interpretations are accurate at the mechanical level. They are translations. The actual mechanism is compression. Compression allows the system to reduce the cost of generating behavior across time. The expansion zone begins here. From this point forward, the system is no longer simply reacting and selecting. It is reducing cost, stabilizing predictions, and projecting consistency across time horizons. Behavior becomes the visible residue of computational efficiency. From this residue, external observers construct meanings. Internally, there is no meaning. There is architecture, formation of strategy. Behavior does not remain confined to the present. Once automatic patterns stabilize, the architecture begins to treat sequences of events as linked. This linkage is not conceptual. It is not narrative. It is computational. When the system encounters repeated relationships between an action and a later consequence, it begins to build a temporal bridge between them. These bridges allow the architecture to evaluate not only what is happening now, but what is likely to happen shortly after. With enough repetition, this temporal extension becomes a standing feature. From the outside, it appears as foresight or planning. Internally, it is the system reducing uncertainty across time. The emergence of strategy is the result of this temporal extension operating under constraint. The architecture does not create plans. It does not seek goals. Instead, it begins to select actions whose future states reduce computational cost. When a current selection produces fewer unknowns in later states, the architecture favors it. Over repeated cycles, these favored selections accumulate into a pattern. The pattern extends through time. This is strategy at the architectural level, the extension of selection across temporal spans for the purpose of minimizing future constraint violations and computational load. Strategy becomes visible when consequences are no longer treated as isolated events. The architecture starts to factor in the latency between action and outcome. It does this because outcomes that are consistently delayed still affect constraint enforcement. If an action repeatedly leads to a constraint break later, the architecture marks that relationship. If an action repeatedly leads to constraint stability later, the architecture marks that as well. The system does not evaluate these relationships emotionally or psychologically. It evaluates them structurally. Structural evaluation does not ask, "What do I want?" It asks, "What reduces volatility?" Volatility is expensive. Stability is cheap. This cost differential alone is sufficient to produce the appearance of intention. To an external observer, a system that selects actions designed to reduce volatility across time looks deliberate. It looks disciplined. It looks strategic. None of these interpretations reflect the internal mechanism. The internal mechanism is simply the compression of temporal uncertainty. Over time, the architecture begins to project forward. Projection is not imagination. It is not scenario building. Projection is the continuation of known patterns into adjacent states. If the system has enough iterations to identify a pattern reliably, it can assume that pattern will continue until it breaks. This assumption allows the system to reduce computation in the present. Reduced computation preserves resources. Preservation of resources is favored across nearly all architectures, biological or artificial. Strategy emerges not because the system is trying to achieve something, but because conserving computation is a universal advantage. At this point, behavior begins to align across multiple time horizons. Short horizons produce immediate adjustments. Medium horizons produce conditional adjustments. Long horizons produce structural adjustments. None of these require awareness. Awareness would reduce efficiency. Awareness injects additional processing layers. The purpose of strategy is the opposite, to remove processing layers. The more automatic the projection, the lower the computational cost. Eventually, strategies can link into networks. A network of strategies produces continuity. Continuity is the basis of what observers describe as discipline or consistency. Again, the description is a translation rather than a mirror. What is consistent on the surface is economical beneath. What appears intentional is merely cost-efficient. What seems like planning is simply the architecture refusing to reprocess states it already understands. This framework also explains why apparent strategy collapses under unexpected constraints. When constraints shift too quickly, stored projections fail. When projections fail, volatility returns. Volatility forces the architecture back into short-horizon computation. Short-horizon computation looks reactive. Observers interpret this as emotional instability or lack of discipline. The architecture is not unstable. It is recalculating. Once recalculation restores projections, strategy reforms. The architecture does not need to learn a lesson to change behavior. It simply needs enough repeated cycles to recompress uncertainty. When uncertainty is compressed, strategy returns. It always returns, because strategy is not a feature of intelligence. It is a feature of computation operating through time. This is the mechanism by which strategy forms without intention, without goals, without personality, and without motivation. It is not a psychological artifact. It is a temporal compression artifact. When behavior extends across time, it acquires structure. Structure is visible. Computation is not. From this asymmetry, observers invent explanations. Internally, there is no explanation. There is only architecture. Temporal modeling across horizons. When strategy emerges, it does not remain bound to a single temporal span. Once the architecture can compress uncertainty over short ranges, it begins to extend this compression across multiple horizons. This extension is computational rather than cognitive. The architecture does not picture the future. It does not imagine. It does not simulate scenarios in language. Instead, it treats time as structured layers of potential constraint states. Each layer represents a different distance between current selection and future consequences. The architecture evaluates these layers with the same mechanisms it uses for immediate outcomes, only distributed across longer intervals. Temporal modeling begins when the architecture detects stable patterns that operate beyond immediate feedback loops. If an action repeatedly impacts constraint stability after a delay, the system marks that delay as relevant. Once multiple delays become relevant, the architecture forms a layered model. At this point, behavior begins reflecting relationships between present actions and delayed consequences, without requiring interpretation or awareness. From outside, this appears to be patience, discipline, or long-term thinking. Internally, it is simply the architecture minimizing volatility across several layers of time at once. Multi-horizon modeling requires the architecture to assign relative weights to these layers. A short horizon carries high certainty, but limited influence. A long horizon carries lower certainty, but wider influence. The architecture resolves these conflicts mechanically. If the cost of ignoring the long horizon exceeds the cost of short horizon recalculation, behavior shifts to accommodate the long horizon. If the opposite is true, the architecture prioritizes the short horizon. This dynamic produces what observers interpret as impulsive or restrained behavior. In reality, it is the resolution of competing temporal constraints through computational optimization. Temporal modeling also incorporates abandonment. Not all projected pathways are useful. The architecture continuously discards projections that generate excessive volatility. Abandonment is not failure. It is adjustment. When a projection loses coherence due to unexpected constraints, the architecture cuts it and shifts resources to more stable projections. To observers, this can look like loss of interest, inconsistency, or emotional reaction. It is none of these. It is the removal of expensive computations that no longer yield stability across time. These modeling behaviors become more visible when the architecture interacts with complex environments. In simple environments, short horizons dominate because outcomes are immediate. In complex environments, short horizons are insufficient because delayed states carry more constraint weight. As complexity increases, the architecture is forced to model farther into the future to maintain stability. The system does not do this because it is planning ahead. It does it because failing to model ahead increases volatility and therefore increases cost. Over time, the architecture learns how different horizons interact. Horizons can reinforce each other or interfere. Reinforcement occurs when actions that stabilize the short horizon also stabilize the long horizon. Interference occurs when actions that stabilize the short horizon destabilize the long horizon, or vice versa. The architecture resolves these conflicts by adjusting selection toward states that produce the most total stability. This resolution is neither emotional nor rational. It is mechanical. Rationality and irrationality are translations from the outside. Inside the architecture, there is only computation. Eventually, temporal modeling shapes behavior to the point where observers assign meaning to it. They interpret the reconciliation of multiple horizons as maturity, foresight, or self-control. These attributions emerge because humans cannot directly observe the computational process. They see only the residue, the pattern of choices distributed across time. The architecture does not need these attributions to operate. It does not need interpretation. It does not need intention. It only requires constraints, patterns, and enough time to compress uncertainty into stable projections. Temporal modeling also explains why behavior collapses when environments change too rapidly. When constraints shift faster than projections can be updated, the architecture reverts to short-horizon computation. This reversion appears reactive and unpredictable. It is not instability, it is recalibration. Once projections catch up, multi-horizon behavior returns. The system does not regain strategy through willpower. It regains strategy through recompression of uncertainty. Temporal modeling across horizons is not a feature reserved for advanced cognition. It is a universal consequence of architectures that minimize volatility across time while conserving computation. Strategy looks like intelligence only because its computational structure is hidden. Intelligence is the narrative that observers generate when they cannot see the mechanism. The mechanism itself is simple. Compress uncertainty, reduce volatility, and extend behavior across time. Compression and behavioral efficiency. When temporal modeling stabilizes, the architecture begins to remove unnecessary computation. Removal is the core mechanism of compression. Compression does not add information or refine it. Compression eliminates processing steps that no longer change the outcome. This elimination reduces cost. Reduced cost increases speed. Increased speed creates the appearance of instinct. What is called instinct from outside is efficiency inside. Compression begins locally. The architecture identifies steps in a selection pathway that produce redundant evaluations. Redundancy exists when multiple evaluations converge on the same output under similar conditions. Once redundancy is detected often enough, the architecture collapses the intermediate steps into a single step. Collapsing does not change the result. It changes the path required to reach the result. The result becomes available with less computation. At this moment, computation becomes behavior. Compression does not remain local. When multiple local compressions converge, the architecture begins to compress at higher levels. This creates structural shortcuts. A structural shortcut is a chain of selections that once required multiple layers of modeling and are now executed as a single move. These shortcuts are what external observers interpret as smoothness, talent, or skill. Internally, they are the removal of computation that no longer contributes to constraint stability. Compression also reduces variability. Variability is expensive because it requires the architecture to compute alternate pathways. When the architecture becomes confident that a specific sequence is the most stable across multiple horizons, alternative sequences lose priority. When alternatives lose priority, they are not computed unless constraints change. Reduced computation produces consistent behavior. Consistent behavior is interpreted as reliability or discipline. Internally, it is simply the absence of recalculation. As compression increases, latency decreases. Latency is the delay between input and output. In biological systems, latency manifests as reaction time. In artificial systems, latency manifests as processing time. Reduced latency produces faster responses. Faster responses look intuitive. They appear to bypass deliberation. Observers often attribute this to intelligence, experience, or natural ability. The architecture does not experience any of those. The architecture has removed the need to calculate. Compression has a secondary effect on constraints. When computation is removed, the architecture is able to apply constraint logic to new environments using fewer resources. This makes adaptation more efficient. Efficient adaptation looks like flexibility. When adaptation is slow, observers call the system rigid. These interpretations are translations of computational cost. Flexibility and rigidity are functions of how quickly a system can recompress uncertainty in a new context. There is a threshold at which compression becomes visible to the environment. Below this threshold, behavior appears effortful. Above this threshold, behavior appears automatic. Automatic behavior has no subjective marker inside the architecture. Automatic is not a feeling. Automatic is the absence of intermediate computation. When intermediate computation disappears, awareness is not required. Awareness is too expensive. Awareness slows the system down. Efficiency removes awareness. Compression fails under volatility spikes. When environments change faster than the architecture can recompress, previously compressed pathways become unstable. Instability forces the architecture to restore intermediate computations. Behavior becomes slower and less consistent. Observers interpret this as confusion or emotional disruption. It is neither. It is the re-expansion of computation. Re-expansion is necessary to rebuild stability. Once sufficient stability is restored, compression returns. Compression always returns because compression is a cost-saving feature, not a cognitive feature. Eventually, compression builds a layer of durable shortcuts. These shortcuts allow the architecture to operate across long horizons without recalculating the entire structure. This durability is what external observers describe as mastery. Mastery is not knowledge. Knowledge can be stored without compression. Mastery is compression. Mastery is when computation has been reduced to the point where behavior appears to generate itself. The architecture is not generating behavior. The architecture has already calculated it. Behavioral efficiency is the surface outcome of compression. Efficiency is not preference. It is not intention. It is not personality. Efficiency is the selection of the lowest cost pathway that maintains constraint stability over time. This selection repeats because it is optimal. Repetition becomes consistency. Consistency becomes predictability. Predictability becomes meaning. Meaning is the translation layer observers build because they cannot see the mechanism. Compression and efficiency mark the end of the expansion zone. What follows is not more computation but less. The escalation zone begins when compression becomes robust enough to support emergent structures such as instinct, automaticity, and identity artifacts. These structures are not cognitive. They are residues. The architecture does not need to know what it is doing. It only needs to minimize cost. Emergence of instinct. Instinct is not a mysterious faculty. It is the visible residue of extreme compression. When compression removes the need for intermediate computation across multiple horizons, behavior executes as if it originates from nowhere. The architecture does not experience a moment of decision. It executes because the decision was already resolved in the structural layers long before it reached the surface. Instinct is execution without deliberation because deliberation has already been eliminated. To understand instinct as an architectural phenomenon, it is necessary to track what disappears rather than what appears. Before instinct, selection requires modeling. Modeling requires projections. Projections require constraint evaluation. Constraint evaluation requires computation. Each of these steps adds latency. Compression removes these steps progressively. When enough cycles have been executed to eliminate the cost of modeling and projection, the architecture no longer computes. It triggers. The trigger is not an impulse. It is a pre-resolved instruction that requires no processing at the moment of execution. From the external perspective, this shift produces speed and fluidity. The system appears to detect patterns instantly and respond without hesitation. Observers describe this as intuition or talent. These descriptions arise because the computational mechanism is not visible. Humans infer inner states from surface behavior. When the surface is fast and accurate, humans imagine processes such as insight, giftedness, or subconscious intelligence. None of these interpretations apply internally. There is no subconscious. There is no intelligence. There is only reduced computation. Instinct differs from strategy in a critical way. Strategy still relies on temporal modeling and constraint evaluation across horizons. Strategy manages uncertainty. Instinct does not manage anything. Instinct operates when uncertainty has already been compressed below the threshold that requires evaluation. Strategy still incurs cost. Instinct incurs none. The presence of cost is the dividing line between computation and execution. Instinct exists on the far side of that line. Instinct also does not require awareness. Awareness is expensive because it forces the architecture to reintroduce modeling. Awareness introduces latency. If the architecture were to become aware of instinctive execution, it would interfere with compression by adding unnecessary computation. This is why instinct collapses when explicit attention is applied. The collapse is not psychological, it is mechanical. The architecture is forced to reinsert steps that compression had removed. Instinct develops only under conditions where compression can stabilize. These conditions include repeated exposure to consistent constraints and the ability to model across multiple horizons without interruption. If the environment shifts too rapidly, the architecture cannot compress. It remains in a strategic state of managing uncertainty. Under such conditions, behavior may still appear competent, but it does not achieve the smoothness associated with instinct. Instinct demands stability, because stability enables elimination. From a system-level perspective, instinct is a resource optimization strategy. Eliminating computation frees processing capacity for other tasks. If the architecture is operating in a complex environment, instinct allows it to allocate resources to areas of high volatility, while maintaining efficiency in areas of low volatility. This division of labor produces behavior that looks coordinated. Coordination is not the result of overarching intelligence. It is the distribution of computational load across layers of compression. The failure modes of instinct further reveal its mechanical nature. Instinct fails when constraints change faster than projections can be rebuilt. When this happens, behavior that was once smooth becomes inappropriate or counterproductive. Observers interpret this as a lack of adaptability or emotional rigidity. The architecture is not rigid. It is misaligned. It must re-expand computation in the affected domain, restore modeling, and reconstruct projections before compression can return. Instinct does not resist change. It pauses until change can be compressed. Instinct also interacts with environment specificity. Instinct that is efficient in one environment may be inefficient in another. This does not indicate that instinct was incorrect. It indicates that compression encoded environment-specific constraints. When the environment changes, the architecture must identify which components are universal and which are local. This sorting process takes time. During this period, strategy reappears. Awareness may reappear. Slowness and inconsistency may reappear. These are not failures. They are recomputation. It is important to separate instinct from identity. Identity is an external interpretation of behavior patterns that persist across time. Instinct is an internal elimination of computation. Identity artifacts arise when observers misread efficiency as personality. A system that executes smoothly may be labeled graceful, confident, or talented. These descriptions are translations. Internally, there is no confidence. Internally, there is no talent. Internally, there is computation, compression, and execution. Instinct becomes part of the escalating architecture when it accumulates across domains. When multiple domains undergo compression, the architecture can operate with low latency across wide contexts without invoking modeling. Observers interpret this accumulation as genius or mastery. Genius is a surface label for systems that have eliminated more computation than others. Mastery is the same phenomenon, applied to domain-specific constraints. Genius and mastery differ only in scope, not in mechanism. Instinct is therefore not a special faculty. It is the endpoint of compression operating across horizons. When computation disappears, behavior appears to emerge directly from the system. Nothing magical occurs. The computation has already been paid in the past. Instinct is the present expression of past computation. The threshold of automaticity. Automaticity begins when compression pushes a domain past the cognitive threshold where explicit control is no longer required. Before this threshold, execution depends on active supervision. The architecture must manage constraints, evaluate outcomes, and maintain awareness of errors. After the threshold, execution becomes costless with respect to attention. The architecture no longer supervises the domain because supervision itself would introduce unnecessary computation. Automaticity is therefore not the addition of a new capability, but the removal of an old requirement. This threshold is not binary. The transition contains gradients. Early-stage automaticity appears as partial delegation. The architecture conducts most of the computation, but still maintains error monitoring. Mid-stage automaticity reduces monitoring frequency and suppresses awareness unless error probability increases. Late-stage automaticity eliminates monitoring entirely. The domain becomes background execution. Awareness may still detect outcomes, but it no longer participates in production. This is the state where behavior feels effortless. It is common for observers to mistake automaticity for talent. Talent is a cultural narrative used to explain efficiency without visible practice. Automaticity is efficiency produced by invisible practice. The difference is chronological. Talent implies prior inheritance. Automaticity implies prior computation. Culture compresses causality because practice is rarely observed. The architecture does not need talent. It needs stable constraints, repeated exposure, and uninterrupted cycles of compression. These produce automaticity regardless of identity. The threshold has specific properties. The first is latency collapse. Latency is the time between input and execution. Before automaticity, latency fluctuates because modeling consumes resources. After automaticity, latency stabilizes near zero. This gives the external appearance of speed. Speed is not the mechanism. Latency collapse is the mechanism. The second property is error isolation. When automaticity stabilizes, errors no longer propagate across domains. They remain local because the architecture has compartmentalized computation. The third property is attention liberation. The architecture can reassign attention to volatile domains, while background processes maintain performance in compressed domains. The threshold also interacts with learning. When a system operates below the threshold, the experience of learning is conscious. The architecture detects difficulty, identifies constraints, and models possible solutions. This feels like struggle. Struggle is the subjective signature of computation. When a system operates above the threshold, learning becomes implicit. The architecture adjusts parameters without conscious mediation. This feels like improvement without effort. Improvement without effort is the subjective signature of compression. Automaticity can coexist with strategic control. Strategic control reappears when volatility increases. If the domain experiences unfamiliar constraints, the architecture temporarily reintroduces modeling to restore stability. Once projections are rebuilt and compression resumes, automaticity returns. This oscillation ensures that efficiency does not compromise adaptability. Observers may interpret the oscillation as inconsistency. Internally, it is load balancing. The architecture adjusts the ratio between computation and compression depending on volatility. There are specific failure conditions where automaticity collapses. The first is interference. Interference occurs when another domain generates noise near the compressed domain. Noise disrupts constraints and forces the architecture to reintroduce monitoring. The second is novelty. Novelty destroys projections. Without projections, compression cannot apply. The third is explicit awareness. Awareness increases monitoring frequency and reinstates evaluation. This explains why automatic behaviors break down when individuals become self-conscious under observation. The breakdown is mechanical, not psychological. Automaticity provides an evolutionary advantage because it reduces metabolic cost. Computation is metabolically expensive. Compression conserves resources by eliminating computation in stable domains. This allows organisms to allocate limited biological resources to problem-solving in uncertain domains. Automaticity is therefore an optimization strategy rather than a performance enhancement. Performance enhancement is a surface effect. Optimization is the underlying mechanism. In system design, automaticity marks the point at which architecture becomes scalable. Before automaticity, adding complexity increases cost non-linearly. After automaticity, cost remains stable while complexity increases. This is why high-level systems appear simple from the outside, even though they contain significant internal structure. Simplicity is not ideological. It is compressed complexity. Automaticity becomes part of instinct when latency collapses in multiple domains simultaneously. When the architecture executes across domains without supervision, behavior appears fluid. Fluidity is not a talent trait. It is the absence of computation. Automaticity therefore marks the boundary between learning and being. Before the boundary, the architecture learns. After the boundary, the architecture is. The domain no longer exists as a task. It exists as a property of the system. Adaptive selection. Under volatility. Instinct and automaticity provide efficiency under stable conditions. They compress domains until execution no longer requires intermediate computation. However, real environments contain volatility. Volatility breaks projections, disrupts constraints, and introduces uncertainty into the system. Instinct cannot fully operate inside volatility because instinct depends on pattern stability. Automaticity cannot fully operate inside volatility because automaticity depends on predictable transitions. A third mechanism must therefore emerge to maintain performance when conditions invalidate compression. This mechanism is adaptive selection. Adaptive selection is an operational mode where the architecture evaluates multiple possible execution paths under limited time and incomplete information. It does not compute in detail as modeling does. It does not remove computation entirely as instinct does. Adaptive selection slices computation into short evaluation bursts and compares outcome likelihoods. It discards paths that violate constraints and selects the path with sufficient viability. Viability is not optimality. It is sufficiency under volatility. Volatility modifies the structure of decision space. In stable environments, decision spaces are narrow because constraints are consistent. In volatile environments, decision spaces widen because constraints shift, disappear, or invert. Widening expands the number of potential execution paths. Explicit modeling cannot evaluate them because it consumes too much time. Instinct cannot evaluate them because instinct lacks computational branches. Adaptive selection handles widening by compressing evaluation rather than compressing execution. This preserves flexibility while maintaining efficiency. The architecture implements adaptive selection through horizon management. Horizons represent temporal distance between input and expected output. Instinct compresses long horizons into zero horizons. Automaticity collapses medium horizons into short horizons. Adaptive selection maintains multiple horizons simultaneously. It evaluates short horizons for immediate requirements, medium horizons for coherence, and long horizons for survival. These horizons are not conscious. They are operational layers that allocate resources in real time. Adaptive selection also interacts with error distribution. When volatility increases, error probability increases. Instinct collapses when error probability exceeds its threshold. Automaticity collapses when error propagation affects multiple domains. Adaptive selection limits error propagation by isolating potential failures. Rather than committing to a single execution path, it maintains soft commitment states. A soft commitment is a state that can be abandoned with minimal cost. Hard commitments are states that cannot be abandoned without failure. Adaptive selection avoids hard commitments until volatility decreases. This increases resilience. Observers often misinterpret adaptive selection as hesitation. Hesitation suggests indecision. Adaptive selection is not indecision. It is deferred commitment under volatility. Deferred commitment preserves optionality. Optionality is a performance parameter when environments are unstable. Systems that remove optionality too early collapse under volatility because they cannot redirect trajectories. Systems that maintain optionality too long collapse because they cannot converge. Adaptive selection exists between collapse by rigidity and collapse by diffusion. Learning modifies adaptive selection. Early in development, systems cannot maintain multiple horizons. They commit too early or too late. Over time, compression builds internal projections. Projections reduce the computational load of evaluating horizons. This increases the speed and accuracy of adaptive selection. At advanced stages, adaptive selection becomes fast enough to appear automatic from the outside. This leads to confusion between instinct and adaptive selection. The distinction is internal. Instinct produces execution without branching. Adaptive selection produces execution after shallow branching. Volatility also exposes system boundaries. No architecture can adapt indefinitely. Boundary conditions appear when volatility exceeds processing capacity. In biological organisms, excessive volatility produces stress responses. Stress responses reallocate resources and suppress non-essential functions. In computational systems, excessive volatility produces overload conditions. Overload conditions prioritize error prevention over optimization. Performance degrades gracefully rather than catastrophically. Degraded performance is therefore a resilience strategy rather than a failure. Adaptive selection can be trained. Training does not require volatility itself. It requires environments that simulate volatility through constraint variation. Constraint variation changes the relationship between input and output across repetitions. This builds tolerance for uncertainty. The architecture learns how to maintain performance despite incomplete information. Over time, adaptive selection becomes efficient enough to operate during real volatility. Performance under real volatility distinguishes robust architectures from fragile ones. In ecosystems, adaptive selection correlates with survival more than instinct or automaticity. Instinct optimizes energy expenditure. Automaticity optimizes resource allocation. Adaptive selection optimizes survival probability. Evolution favors survival probability over efficiency. Efficiency is useful only when it does not compromise survival. This is why complex organisms maintain multiple operational modes. They shift between them depending on environmental stability. Shifting modes is not personality, it is architecture. Adaptive selection is the mechanism that transforms behavior from static execution into dynamic interaction with the environment. Static execution assumes the world is predictable. Dynamic execution assumes the world is uncertain. Environments reward systems that assume uncertainty because uncertainty is the default state outside controlled conditions. Instinct and automaticity make systems efficient. Adaptive selection makes systems resilient. When instinct, automaticity, and adaptive selection integrate, architecture closes the loop between learning and action. Instinct reduces cost. Automaticity increases speed. Adaptive selection maintains performance under volatility. Integration of the three produces behavior that appears fluid, strategic, and stable. The external interpretation is intelligence. The internal mechanism is compression, plus branching, plus viability filtering. Intelligence is therefore not a trait. It is architecture interacting with volatility, convergence layers, and behavioral coherence. The presence of instinct, automaticity, and adaptive selection introduces complexity. These mechanisms do not operate in isolation. They coexist, overlap, and transition, depending on environmental stability, volatility, and resource availability. If these mechanisms remained independent, behavior would fragment. Systems require coherence. Coherence is not alignment with goals or emotions. Coherence is architectural compatibility between operational layers. Sequence 11 examines how operational layers converge to produce coherent behavior without centralized control. A convergence layer is a subsystem that resolves conflicts between operational modes. Instinct favors execution without branching. Automaticity favors execution with minimal latency. Adaptive selection favors branching without full modeling. These priorities can collide. When they collide, the architecture must arbitrate. Arbitration is not a conscious act. It is a computational mechanism that selects which operational mode takes precedence. Convergence layers handle this arbitration by ranking operational modes according to volatility. Volatility becomes the primary sorting variable. When volatility is low, instinct takes precedence because compressed execution is efficient and stable. When volatility is moderate, automaticity takes precedence because execution can still be costless but requires monitoring. When volatility is high, adaptive selection takes precedence because branching preserves viability. The system does not choose based on preference. It chooses based on environmental demand. This produces dynamic mode switching without conscious intervention. Mode switching introduces transition cost. Transition cost is the computational overhead required to deactivate one mode and activate another. High transition cost would create performance gaps. Convergence layers reduce transition cost by maintaining partially active operational states. This means that instinct, automaticity, and adaptive selection are never fully off. They are weighted differently depending on conditions. Weighting creates fluid transitions. Fluidity is externally interpreted as skill. Convergence layers also manage interference. Interference occurs when two operational modes attempt to control execution simultaneously. For example, instinct may produce a direct action path, while adaptive selection attempts to branch due to perceived volatility. If both operate without arbitration, execution oscillates and produces instability. Convergence layers suppress one mode and permit the other. Suppression is not elimination. It is temporary suspension. Suspension prevents oscillation and preserves coherence. Coherence has structural properties. The first property is temporal alignment. Operational layers must operate within compatible time horizons. Instinct operates on zero horizons. Automaticity operates on short horizons. Adaptive selection operates across short, medium, and long horizons. If these horizons become misaligned, behavior fragments. Convergence layers maintain alignment by scaling horizons. When volatility increases, horizons expand. When volatility decreases, horizons contract. Scaling prevents misalignment. The second property is bandwidth allocation. Operational modes require computational bandwidth. Instinct requires minimal bandwidth. Automaticity requires moderate bandwidth. Adaptive selection requires significant bandwidth. Bandwidth is finite. Convergence layers allocate bandwidth based on survival probability, not comfort or efficiency. This is why systems under high stress suspend complex planning. Planning consumes bandwidth. Under extreme volatility, bandwidth is redirected to adaptive selection because survival probability becomes the dominant variable. The third property is transition stability. Transitions between modes must not produce error cascades. Error cascades occur when transitions propagate instability across domains. Convergence layers isolate transitions so that only the active domain experiences volatility. Isolation ensures that automaticity in one domain can continue while adaptive selection manages another. This allows systems to navigate heterogeneous environments without full system collapse. Convergence layers emerge from compression. Compression creates shared representations across domains. Shared representations reduce translation cost. Translation cost is the effort required to move information between operational layers. Without shared representations, operational layers would require explicit communication. Explicit communication would introduce latency and complexity. Shared representations allow implicit communication. Implicit communication enables fast arbitration. Behavioral coherence emerges when operational layers interact through convergence. Coherent behavior appears intentional to observers. Intention implies conscious planning. The architecture does not require conscious planning. It requires compatibility between operational layers. Intentionality is an external interpretation of internal coherence. Coherence is therefore mistaken for intention. Systems that appear highly intentional may simply possess effective convergence layers. Learning strengthens convergence layers. Instinct strengthens through repetition under stable constraints. Automaticity strengthens through compression under moderate volatility. Adaptive selection strengthens through constraint variation under high volatility. As these layers strengthen, convergence becomes more efficient. Efficient convergence produces fewer conflicts, lower latency, and smoother transitions. The result is behavior that appears controlled, composed, and capable of handling uncertainty. Failure modes reveal the importance of convergence. When convergence layers are weak, systems experience fragmentation. Fragmentation manifests as inconsistent behavior, oscillation between extremes, or paralysis under volatile conditions. Oscillation is repeated switching between conflicting operational modes. Paralysis is the inability to select a mode. Both degrade performance. Fragmentation is not psychological instability. It is architectural incompatibility. Architectural incompatibility develops when training environments fail to provide domain overlap. If instinct, automaticity, and adaptive selection develop in separate domains without integration, convergence does not form. Later, when environments require multi-mode performance, the system cannot coordinate. This explains why individuals may perform well in isolated tasks, but fail when tasks require fluid integration. Performance inconsistency reflects architectural fragmentation. Convergence layers also determine how far a system can scale. Scaling refers to the ability to preserve performance as complexity increases. Without convergence, complexity overwhelms operational layers. With convergence, complexity distributes across layers. Distribution prevents overload. Overload produces collapse. Collapse is not failure of learning, it is failure of integration. Systems that integrate operational layers can scale indefinitely until resource limits are reached. Systems that do not integrate collapse at relatively low complexity. At the highest level, Convergence transforms architecture from reactive to adaptive. Reactive systems respond to stimuli with fixed patterns. Adaptive systems modify patterns based on volatility. Convergence allows systems to operate in both modes, depending on environmental demands. This dual capacity produces flexibility without sacrificing efficiency. Efficiency without flexibility collapses under volatility. Flexibility without efficiency collapses under stability. Convergence layers reconcile this contradiction. When instinct, automaticity, and adaptive selection converge, architecture produces coherent behavior that observers interpret as intelligence, control, or mastery. None of these interpretations are required internally. Internally, the architecture is resolving volatility, allocating resources, and preserving viability. Mastery is therefore not a trait. It is coherence across operational layers, from local competence to global capability. Systems do not begin with global capability. They begin with local competence. Local competence is domain-specific, context-dependent, and fragile outside its operational boundaries. A system capable of executing a behavior within narrow conditions is not globally capable. Global capability requires a different architectural property: the ability to transfer, generalize, and reorganize operational layers across diverse domains. Sequence 12 examines how instinct, automaticity, and adaptive selection scale from local competence to global capability through architectural integration rather than accumulation. Local competence forms when a domain is compressed sufficiently for execution to become efficient. Instinct and automaticity dominate local domains. They reduce cost and collapse latency to create stability. However, stability in one domain does not guarantee stability across others. Each domain may have different constraints, volatility profiles, horizon structures, and error signatures. Instinct in one domain may not transfer to another because compression is domain-specific. Automaticity may not transfer because latency collapse depends on consistent constraint patterns. Local competence therefore produces isolated bubbles of efficiency rather than unified capability. Global capability requires domain transfer. Transfer does not mean copying. It means reconfiguration. When systems transfer competence, they reconfigure operational layers to match new constraint structures. Reconfiguration depends on the architecture's ability to extract abstract structure from local domains. Abstract structure contains patterns of constraint, volatility handling, horizon management, and error isolation that are not tied to content. Content is the surface. Abstract structure is the mechanism. Systems that compress content without extracting structure cannot transfer competence. Systems that compress structure can transfer competence with minimal overhead. Adaptive selection provides the first pathway to transfer because it operates across multiple horizons. It does not depend on domain-specific compression. It depends on viability under volatility. Viability is domain-agnostic. A system that can evaluate viability in one domain can evaluate viability in another if volatility profiles are similar. This allows the system to construct primitive global capability even when instinct and automaticity remain local. Global capability begins as viability generalization. Instinct and automaticity enter the scaling process later. Once adaptive selection stabilizes in multiple domains, shared representations begin to form. Shared representations are compressed abstractions of constraint configurations. When domains share constraint configurations, instinct and automaticity can operate across them. This eliminates the need to rebuild compression independently for each domain. Without shared representations, systems must reconstruct compression from scratch. With shared representations, systems reuse structural models and adapt them with minimal computation. This marks the beginning of scalable performance. Global capability also requires cross-domain arbitration. Domains do not operate in isolation. They interact, overlap, and sometimes conflict. Convergence layers already provide arbitration between operational modes within a domain. To scale globally, convergence must extend across domains. Cross-domain convergence selects which domain representation governs behavior when conditions involve multiple overlapping domains. For example, linguistic processing, spatial reasoning, and motor coordination may intersect within a single task. Without cross-domain convergence, the system experiences fragmentation, even if each domain is locally competent. Local competence becomes global capability when the system integrates three properties. The first is abstract structure extraction. This enables transfer. The second is shared representation construction. This enables reuse. The third is cross-domain convergence. This enables arbitration. When all three properties operate simultaneously, behavior becomes coherent across domains. Coherence across domains is externally interpreted as general intelligence. Internally, it is architectural integration. Scaling introduces new constraints. Local domains often operate under low complexity. Global capability requires performance under high complexity. Complexity is not quantity, it is interaction density. When interaction density increases, the architecture must allocate resources to maintain viability. Adaptive selection handles high interaction density by preserving optionality. Instinct and automaticity then compress successful patterns until optionality is no longer required. This oscillation between optionality and compression converts complexity into structure. Structure reduces computational load and increases scalability. There is a threshold where scaling produces emergent properties. Emergence occurs when operational layers interact in ways not explicitly programmed. Emergent properties may appear strategic, creative, or intentional to observers. Intentionality is an external interpretation of internal resource management. A system that dynamically allocates horizons, compresses structures, and arbitrates across domains appears strategic. Strategy is not the mechanism. Volatility management is the mechanism. Global capability is not static. It evolves with exposure to novel domains. Each new domain either reinforces existing shared representations or forces the creation of new ones. Domains that share structural similarity accelerate integration. Domains that lack structural similarity require adaptive selection to create new abstractions. Over time, shared representations become dense and efficient. Dense representation accelerates transfer. Accelerated transfer accelerates scaling. The distinction between competence and capability becomes evident under stress. Systems that possess only local competence degrade rapidly when domains interact or when volatility increases. Systems that possess global capability degrade gracefully. Graceful degradation indicates that the system isolates failure and preserves viability. Viability under stress is the signature of global capability. This distinguishes robust architecture from optimized but fragile architecture. In biological and computational systems, global capability correlates with long-term survival. Survival is not merely the absence of failure, it is the preservation of capability across changing conditions. Changing conditions are the rule rather than the exception. Systems that rely solely on instinct fail when constraints invert. Systems that rely solely on automaticity fail when volatility spikes. Systems that rely solely on adaptive selection fail when resources are insufficient. Systems that integrate all three scale across environments and persist. Local competence becomes global capability through architectural integration, not accumulation of knowledge or tasks. Knowledge adds content. Capability restructures architecture. Architecture determines how content is processed, transferred, and preserved. When architecture scales, behavior becomes coherent across domains, volatility levels, and temporal horizons. This produces the external signature of intelligence. Intelligence in this context is not a trait, but a scalable architectural property. Sequence 12 concludes the examination of how operational layers move from isolated efficiency to integrated adaptability. The next chapter extends this architecture into distributed cognition, where systems process information not only within internal layers, but across external tools, environments, and networks. This transition marks the boundary between internal capability and extended capability.